that you invited me to give this talk, and I'm looking forward to hearing the questions from you and your students. The work I'm going to tell you about today involves developing new routine analytical chemistry that's enabled by modern benchtop XAFs or ZAPs, people call it, and XES spectrometers. And some of the applications I'll talk about involves batteries, catalysts, nanophases, new LEDs, and more. I've had the advantage of some great collaborators at many institutions during this work, including a great team of students in my group and students and collaborators, especially in the chemistry department at UW, friends and colleagues at Los Alamos, University of Iowa, Argonne Labs, Pacific Northwest National Labs, SUNY Binghamton, NIST, and NREL. And we've been fortunate to have funding from a number of different channels, which has helped this research move forward. Jeff's told me that there's a very broad audience across undergrad, graduate, and beyond. And so I wanted to take a minute first and just ask, why do you start a project, right? I'm telling you about a research program even, not just a project. And so it's always good to ask, why do it? And whenever you're considering that, the first thing is to remember that you've been told if it ain't broke, don't fix it. And that turns out to be really great advice for when you're planning a research project, but you have to flip it around a little bit and say that your goal is to find broken, worthwhile things that you yourself can fix. So what does it look like in science and engineering when something's broken? Well, the first thing is there could be a question of range. You might need to expand existing methods to a new problem, or expand the parameter space of some existing method for known problems so you can get better and broader data on a problem you're already interested in. There also could just be a question about tools. You might need new methods for new problems, or a method might need improved performance for more reliable or broader use. And so when you do a research project in one of these categories, your goal is to have impact in science or society or both. But when you have this category of problem, your impact is usually within the specialty that the problem is based in. Not always, but usually. Another thing you can ask is, what can you do to increase the access to tools? And so that's sort of a different thing that can be broken. And if access is insufficient, then increasing it enhances existing R&D. And if you can disruptively increase access, then that tends to cross barriers between fields that in the past maybe didn't have much in common in how they approach their problems. So again, when you're messing around with access to tools, the impact often crosses specialties. All right, so what does that have to do with today's talk? So it's useful to think about instrumentation. Let's talk about tools in the sense of instrumentation on this kind of a plot, where the horizontal axis is a logarithmic scale of capability or quality, where general purpose is 10 times better than introductory in some important metric, specialized 10 times better than general purpose, and so on. And unfortunately for us, the vertical axis, which is how often can you get access to an instrument, is also logarithmic, spanning many orders of magnitude between you'll very rarely be allowed to use world-class equipment, but maybe you'd very easily be allowed to use introductory equipment. So along those lines, let's talk about an example we all know, personal transportation. So if we tried to fill out this figure for personal transportation, we might start with Hello Kitty flip-flops as an example of introductory level personal transportation. And we can all get shoes and go for a walk. Then general purpose, you could have your Dora the Explorer tricycle. Undergraduate personal transport, this is Professor Terry's car. It's really a very nice ride. And going up from there, you've got university presidents. They got places to be. And really, the only step up from university presidents is Elon Musk. So you have this inverse relationship between how easy is it to get access to some level of capability for the thing you care about, in this case, personal transportation. So this inverse relationship is very common. It's not quite a supply-demand curve, but it's related. And if instead of talking about personal transportation, I ask about vacuum systems or vacuum methods like X-ray photoelectron spectroscopy or EELS, or a wide range of X-ray methods, X-ray fluorescence, X-ray diffraction, or NMR, optical spectroscopies, mass spec, and so on, that inverse relationship still holds. There is or could be easy access to introductory level equipment, but there's certainly going to be very difficult and infrequent access to world-class equipment. So again, this holds for the overwhelming majority of scientific methods, but it doesn't hold for X-ray absorption, fine structure, and X-ray emission spectroscopy. So here, right, you have specialized and world-class capability I'll describe in a second, which does have the inverse relationship, and then access basically falls off a cliff. So first, let's ask, for X-rays, what does it mean, specialized and world-class? And spanning specialized and world-class is the synchrotron X-ray sources, such as the Advanced Photon Source, there's a picture of here, which is located outside Chicago at Argonne National Labs. Or X-ray free electron lasers would be strictly world-class, such as this one in South Korea at Pohang. All right, these are national user facilities. They cost $200 million to $1 billion to build. They emphasize scientific discovery, and they're really very, very highly successful engines for discovery. They have tens of thousands of research articles published per year when you add up the output of the 24 or 25 synchrotron or XFELs around the world. But also getting access to them is highly competitive. Experts in the field who go and apply and say, please let me come and use the X-rays. Well, the oversubscription is between about 3 times and greater than 20 times. And that's for experts working, in the field, working on cutting edge research. And so there's a real access shortage. And coming back to this figure, you say, okay, yes, there's an access shortage here, but boy, something just looks broken down here. So as of this month, there's about 190 synchrotron beamlines that support XAFs at least sometimes. And each of the big round buildings, the synchrotrons, can have up to 60 X-ray beams operating at the same time. So that's why this number is so much larger than the number of big round buildings. But down here, the kind of systems I'm going to tell you about today, there's only about 25 modern tabletop hard X-ray systems in the world, and maybe a few dozen higher harmonic generation or laser plasma systems for working at lower energies that I won't get into today. So there's a real imbalance with 190 here, 20 here, and this is supposed to be a logarithmic scale. So if we had a mature market, we would have expected there would be maybe thousands of laboratory XAF systems, and there isn't. So we have a hypothesis that says that 99% of all potential XAFs and XCS applications can happen in the lab, and those applications are not presently being done at the synchrotron. And they would include education, routine analytical chemistry for environmental studies or material studies, industrial quality control, and regulatory compliance. Those are things you basically can't go to the synchrotron for because it's not why the synchrotron is there. The synchrotron is there for scientific discovery, not for routine analysis. All right, so today I'm mostly going to tell you about our work to try to fill in this category of sort of general purpose to a bit specialized apparatus that doesn't require a synchrotron. And it seems likely that by the end of 2023, there could be certainly more than 100, maybe as many as 200 of these kinds of systems out in the world. And it's interesting to ask what's going to be the applications in research and also what will be the social benefit. I'll also very briefly tell you about a new project to try to fill in this niche, which is going to require a very inexpensive, simple spectrometer that can be used in teaching. All right, so I'm going to pause for a minute That's the big picture motivation. And so do you have any questions before I go to this sort of formal technical presentation?
Nothing in the chat window so far.
Okay. All right. So let me move on then. So here's the outline. I'm going to give you some background on these two techniques first. And then I'll tell you about our work with hard X-rays, then lower energy X-rays. I'll briefly talk about teaching XAFs, and then I'll conclude. So here's an energy level diagram for an atom in a molecule or in a solid. And we have the atomic states, 1s, the core levels, 1s, 2s, 2p, and so on, up to the Fermi level, and occupied states below the Fermi level, unoccupied states above the Fermi level. If I bring in a photon now, I might grab an electron and kick it out of the 1s level and take it up to an unoccupied state if the photon has enough energy. And then Einstein tells us that the kinetic energy of the photoelectron will be equal to the energy of the photon minus the binding energy of the atomic orbital. So that's the basis for X-ray photoelectron spectroscopy that, being in the AVS, many of you probably know about. And there you would use an electron energy analyzer then to determine the kinetic energy spectrum of the electrons coming off your material. And knowing the binding energy, you could then, knowing the photon energy, you could then infer the binding energy for all the different orbitals that you cared about in your system. And this is very useful for oxidation state analysis, and more advanced versions such as ARPES can map out Fermi level electronic structure, which is quite a big deal these days, especially on 2D materials. But there's another way to play around with this Einstein photoelectric equation, and that is you can say, all right, whatever the binding energy is, I'm just gonna take one orbital, let's say the 1s, and I'm gonna ask, how does the probability for photon absorption vary as I scan a monochromatic X-ray beam? So when you scan the incident photon energy, you're also scanning the electron kinetic energy, right? Bigger photon energy at fixed binding energy means bigger kinetic energy. But you guys know that as the kinetic energy goes up, the momentum goes up, which means the de Broglie wavelength of the electron goes down. So you're scanning the electron wavelength. And if you start asking yourself what happens to that electron wave, well, it's going to scatter off of neighboring atoms. And as you scan the wavelength, you can expect to see alternating constructive and destructive interference from that scattering process. So you end up having an element-specific electron interferometer inside your sample. In the simplest treatment, you can Fourier transform the wiggles and the appropriate processing. And from that, you learn about the spacing between your central atom, whatever element whose 1s shell, let's say you're tickling, and its neighbors, first shell, second shell, third shell, and so on. So this is a strictly local probe that doesn't require crystallinity. By contrast, here's X-ray diffraction. Now you take the photon wavelength to be comparable to atomic spacing, and the lattice planes act as the basis for an interferometer. And what you get out is the Fourier transform of the spacing between crystal planes of all atoms in the material. Most applications of X-ray diffraction require crystallinity. So right away, that's going to tell you there's a couple important differences between these methods. The XAFS doesn't require crystallinity, and the XAFS is element specific. On the other hand, the XAFS is local, whereas the diffraction is global. And depending on the problem, you may want one or the other. So let's actually look at the X-ray absorption for a system. Let's say cobalt. Here's a table of the binding energies in electron volts for the indicated shells, 1s, 2s, and so on. And if I look at the absorption coefficient of the photons as a function of photon energy, indeed, I see bumps, or at least onsets of bumps, at each of the binding energies from the X-ray data book. All right, so Einstein was right, which is always nice. But if we look more closely now near the 7709 EV binding energy of elemental cobalt, I get lots of wiggles. And you know, if anyone asks you what is a spectroscopist's job, the answer is to look at wiggles. And so I've got wiggles here. So this is a good day. And these kinds of wiggles are the X-ray absorption fine structure. The F and S is fine structure in XFs. And they can be interpreted. The material here is a battery material, lithium-ion battery material, lithium cobalt oxide. And the first little blip down there isn't noise. It's telling you something about the coordination symmetry around the cobalt, and possibly the something about the total 3D local magnetic moment from the cobalt ion. The next shoulder refers to how much lithium is in the lithium cobalt oxide. This big peak from the cobalt 4p states can tell you about damage to the material, such as from overcharging. And then all the wiggles that keep going on for several hundred EVs are what you would analyze to get the distances to nearest neighbors. Okay, but I kind of cheated because I excited an electron out of a core level, and then I didn't tell you what happens to that vacancy. So that vacancy in a deep core level can only live for about a femtosecond before some other electron is going to fall down and fill that hole. And for cobalt, about 2/3 of the time, that'll give you an Auger process that kicks off electrons. But about 1/3 of the time, you'll get X-ray fluorescence. You'll have a radiative decay from some state down to the 1s. And so that fluorescence, if you study it with very high energy resolution, as I'll show you, tends to get called X-ray emission instead of X-ray fluorescence for historical reasons. And there's lots of ways to have this de-excitation down to your core level. So this is a molecular orbital cartoon for a transition metal bonded to a lighter ligand. And you can see I've labeled a whole bunch of possible transitions to either metal 1s vacancies or ligand 1s vacancies. And they have names. K alpha is 2p to 1s, K beta is 3p to 1s, and V to C means valence to core. And you use them for different reasons. These core-to-core transitions can tell you about oxidation state and spin state, and they're really similar to X-ray photoelectron spectroscopy, except that they're bulk sensitive, whereas XPS is much more surface sensitive. The valence to occupied density of states right near the Fermi level, it's looking at the HOMO. It's looking at the real bonding electrons. And so you can get real information about the chemical bonding when you study the X-ray fluorescence that comes from those transitions. All right, so bottom line is people do these methods to get element-specific measurement of oxidation state, local valence level magnetic moment, coordination symmetry, and so on. I'm going to transition now to equipment and applications, but before I do, are there questions?
Nothing in the chat window yet. Anybody out there have any questions?
All right, I'll continue then. So let's talk about hard X-rays, which for me means kind of 5 to 20 kilovolts. The simplest measurement for X-ray absorption you can do is exactly a transmission absorption measurement, where the absorption coefficient mu is the negative logarithm of the transmission over the incident flux. So here's the cartoon of the experiment. And the simplest question you can ask from the experimental point of view is how many X-rays do I actually need to do a good measurement? So this is a simulation for an iron oxide of a particular thickness. And the bottom simulation is pretty bad, right? But it only has 1,000 incident X-rays at each energy. And then 10,000 incident X-rays and 100,000 incident X-rays and so on. And the data is pretty good at 100,000 incident X-rays per data point. You might want a little bit more counting here. You might see there's a double bump there. It's hard to see at the 10 to the 5 data. But the general message is you don't need a lot of photons if you have a concentrated sample like this. So going back to that figure I started the talk with, it suggests that an introductory piece of equipment might only have 1,000 or 10,000 photons per second in a 1 eV band. And that would let you get a good spectrum in a couple hours to a day. A general purpose instrument would be more like 10 to the 5 to a million photons per second in a 1 eV band. And that'll give you a good spectrum in a few minutes to maybe a day if your sample wasn't very concentrated. Well, the synchrotron is at 10 to the 9 to 10 to the 13 photons per second in a 1 eV band. Now, that flux and brilliance is absolutely needed for dilute systems and time-resolved studies and micro and nano imaging, but it's not needed, I'm going to show you, for routine studies where you have a concentrated bulk sample and you're not in a rush. Okay, so what about X-ray emission spectroscopy, right? If we're going to make this practical in the lab, we have to believe the count rate is going to be okay. So up here, I have a synchrotron with an intense X-ray beam coming off, hitting a sample and giving fluorescence. And that goes to a spectrometer. And maybe I'm looking at chromium, and I'm studying these two transitions, the K-alpha-1 and K-alpha-2 with these atomic designations. All right, well, in the lab, I have an X-ray tube, which has an intense X-ray beam coming off of it, hitting a sample, making fluorescence, going to a spectrometer and giving a spectrum. I'm not going to reinvent the spectrometer. I'm going to use the same optics and the same general approaches at the synchrotron. So the only question is, how different is the incident flux? Well, the synchrotron lets you get a monochromatic beam with very high intensity, but even a not very big X-ray tube can give the same flux that's polychromatic. But all that matters is how many photons are above the binding energy of the element you're trying to study, rather than necessarily are monochromatic at that energy. So when you work the numbers, you can get very similar core hole ionization rates in the lab using an X-ray tube as you do at the synchrotron using a very intense collimated monochromatic X-ray beam. So right away, the expectation is that you're going to be able to do an awful lot of X-ray emission spectroscopy in the lab. All right. We had these ideas, and we decided that we should try to copy the world's most successful manufacturer of entry-level apparatus, right? We're looking for something easy. And so we said, all right, we want to copy IKEA. And maybe someday they'll get into XF spectrometers. And the key point is cheap parts that you put together with an Allen key. That was our goal. And so about 7 years ago now, we took a wooden box, we put lead in it, we had a garbage bag with helium in it to decrease air absorption, and we had a happy grad student who was smiling because they could do XFs every day. And the inside of the instrument, you know, X-ray source, optic, detector, it's as simple as it could get. There's rubber bands. And it worked. It took us less than 50 days from the concept to getting first spectra. And we got a whole bunch of papers out of this. I don't want to spend time on this instrument, except to say that right away, we got this data that I showed you earlier. And the red data that has no noise at all was taken at the advanced photon source in probably about 10 minutes. And then the blue data was taken in Seattle with our first prototype system at just 3,000 photons per second. And the data is identical. Yeah, it took us 6 hours, but we got the data that day. All right, so bottom line was it looks like our simulation was right. And for bulk concentrated samples, we don't need a synchrotron. However, again, you do need a synchrotron for dilute samples, time-resolved studies, micro-nano focus, and so on. Emission spectroscopy, again, not quite right away, but pretty soon, we found we were doing the hardest measurements in X-ray emission spectroscopy in the lab. These little bumps identify what the zinc is bonded to. I showed you K-alpha before, meaning 2p to 1s. This is the valence electrons, the chemical bonding electrons falling into the 1s, and it's about 400 times weaker than the main K-alpha fluorescence that you'd use to detect the presence of an element. So it doesn't get much harder than that, but we could do it in the lab. So that smiling student graduated and decided to launch a startup company, EasyZaps. And things, despite COVID, are moving along. And still, hopefully, by the end of 2020, he will have delivered a total of 20 systems around the world. And their system's cleaner and has less rubber bands, so it's easier to explain how this works. You have an X-ray source going to a shining on a sample in this case, creating fluorescence, which goes to a curved silicon or germanium wafer that acts as the dispersing and focusing element and sends one wavelength, maybe with harmonics, but let's say one wavelength back to a detector. And then you scan, you can see there's a translation stage here and a translation stage here. You scan those stages symmetrically to change the Bragg angle on the analyzer and to change the wavelength that gets to the detector. And from that, you build up a spectrum for very high resolution study of the X-ray fluorescence. So there's a system just like this one at IIT now. For XAFs, you have an X-ray source again, and now you aim it straight at the analyzer. And what's going to come off of that is just the wavelength you want and harmonics. That goes through your sample on a sample turret to a detector, and the final detector can reject the harmonics. So you essentially have a scanning monochromatic beam of X-rays in the lab. Okay. This is for experts. These wiggles, they go on forever, and they agree between the lab and the synchrotron. And when you do this Fourier transform method to get the nearest neighbor distances, everything agrees between the synchrotron and the lab. But for you students to learn this technique, you usually go to a short course and have a professor who can help you. And it takes a while to get good at doing this kind of analysis, to be able to use it to analyze new systems. So I'm not going to talk about this huge wiggles anymore. I just want to know, what can non-experts quickly and easily get out of XAFs and XES? All right, well, here's an example. Here's another battery material. This is vanadyl phosphate from our collaborators at SUNY Stony Brook. And this big bump, you would learn if you dug into the quantum mechanics a little bit, only occurs if you have very low coordination symmetry, and also its height tells you the amount of lithiation. So if I looked at a sequence of samples of vanadyl phosphate in a lithium-ion battery, I could look at this bump and I could measure how lithiated is the vanadyl phosphate as I charge and discharge the battery. In general, electrode laminates for batteries are just about perfect samples for these kinds of instruments. And it looks like these kinds of systems are going to accelerate materials discovery for electrical energy storage. We've looked at working batteries. If you crack open your cell phone, you'll eventually get to a battery that looks something like this. It's called a pouch cell. And so we were able to look at the nickel K edge, and the shift in the rise in absorption is telling you how the nickel is actually involved in the redox process inside the battery. And we can do that very quickly and study fast charging in the lab. So hopefully that'll become a new way to do battery testing and to diagnose failures in battery manufacture. There's really simple things too. We had collaborators in chemistry who were making cobalt phosphide nanophases for catalysis. And they had a problem, which was they couldn't really tell from X-ray diffraction or XPS or optics whether they were making cobalt phosphide or cobalt-2 phosphide. So we grabbed reference standards in one of their samples, and look, two of these curves are on top of each other, the blue and the orange curve. And that told us they were actually making cobalt phosphide instead of the green curve, which is very distinct. And so we were able to give them quick feedback that their synthesis method had worked. And that was very useful and led to another paper. A lot of you have probably done X-ray diffraction, and you know that an awful lot of what you do, say with powder diffraction, is looking at the peaks and just asking where they are and looking them up in a database. Well, this is kind of similar. You're just doing comparison to reference standards, and it doesn't take deep expertise, just some patience. We've had several collaborations involving vanadium oxide supercapacitor materials. The idea here is you have these vanadium oxide nanoneedles that are coated with a conducting polymer which both helps with conductivity of the sort of agglomeration of these nanoneedles into an electrode, and also changes their chemistry a little bit and introduces oxygen vacancies, which again helps with conductivity of the vanadium oxide. All right, so here's vacuum
We
measurement.
do have a question.
Yes, okay. I was going to break it down in a second, but go ahead.
Okay, the question is, what are the price ranges on the EasyZaps?
You're going to have to contact them. Since I'm a state employee, I can't talk about sales. I just give them science advice. My apologies.
Oh, no problem. So contact them directly.
Yep. Tell them that you got a 50% off coupon from coming to this talk. That'll go over well. All right. So
we have another question.
Yes, please.
Why is the X-ray power limited to 100 watts?
Oh, it's not limited. It's that the that particular X-ray tube is limited to 100 watts because we wanted something that was air cooled, so that it would be easy to operate and easy to move, which was needed for some of the early monochromator designs. Let's say for the X-ray emission spectroscopy measurements, you could go up to as much as a 4 kilowatt tube. The interior design of the tube changes in a way that you won't really get a 40 times benefit, but you'd probably get another 5 or 6 times count rate by going to the 4 kilowatt tube. Shall I continue?
Yep, thank you.
All right, certainly, my pleasure. Again, we have this vanadium oxide system where we're getting oxygen vacancies, and the oxygen vacancies are central to the good performance of this material in supercapacitors. So the X-ray photoelectron spectroscopy tells us that yes, we're getting oxygen vacancies on the surface, but something we want to know is, were we also getting oxygen vacancies throughout the bulk? Because that could guide us toward new ways of synthesizing and treating these vanadium oxide materials. So again, here's the XPS, and the shift in binding energy, depending on how much you age the system with this conductive polymer, is telling you about a change in oxidation state on the surface. So here, again, on the top, we use XPS, and based on the thickness of the polymer, we get gradually increasing oxygen vacancies and decreasing vanadium 5+. And then we do the Zanes, which is going to be a bulk measurement, because the X-rays will penetrate about 10 microns into a vanadium oxide. And there we see that the oxygen vacancies don't really turn on in the bulk until you have a lot of reaction going on between the polymer and the vanadium oxide. And this is what the data looks like. The analysis is done with linear superposition of reference standards of vanadium 3+, 4+, or 5+ oxides, and the result is really informative for future syntheses of these materials. And we've gotten a bunch of papers out of this, but the key point is using both the vacuum method and the X-ray non-vacuum method. So you can see both the bulk and the surface vanadium valence states change. And the other point is that you can do it every day. So our collaborators in material science would bring over one set of samples, we'd measure them, they'd go back and learn something from that, and then come back a week later with more samples, and then a week later with more samples. And all of the measurements I've shown you certainly could be done at the synchrotron, but they can't be done iteratively, because you get beam time once every 4 months, or once every 6 months, or once every year. Okay, a final hard X-ray example involves hexavalent chromium. So this is bad for people. It causes, it's a strong carcinogen. And so there are regulations in Europe that require, I think it's less than 10,000 parts per million hexavalent chromium in each component of consumer products. Well, you need an industry-accepted standard test method to demonstrate compliance, but for plastics, it's known that the liquid extraction methods are unreliable. So our question was, can we do a non-destructive measurement of the hexavalent chromium in plastics? So some work had previously been done with what are called wavelength dispersive X-ray fluorescence systems, and their energy resolution wasn't very good. They could see some small changes I won't go into between chromium-3 and chromium-6 at about 20 volt resolution. Well, here's our data at 1 volt resolution. So we have 2p to 1s gives two different lines because of the spin orbit splitting of the 2p. And again, spectroscopy is about looking at the bumps. And the bumps are different for chromium-6 and chromium-3. And over here, a little bit different for the chromium-6 and the chromium-3. All right. So if I take my reference standard plastics, these are all different acronyms for reference standards from ASTM or other societies. But they're polyethylene, polypropylene, and PVC with low chromium content, 50 to 1,000 parts per million, where there wouldn't even be a need to test the oxidation state if this is what was being used in commercial products. We were able to do the linear superposition fit between the 3+ chromium and the 6+ chromium and infer what percentage of chromium-6 each sample had. So this suggests using the benchtop XCS as a standard test method for regulatory compliance. I have just a few more slides to show at lower energies. Before I do, are there questions?
Nothing in the chat. Oh, there we go. Here we go. Ideally, in your mind, the main target for these setups would be companies or universities?
Whoever can make good use of them. So far, the universities have jumped more strongly at it than companies have. But a possible reason for that is there's relatively little industrial use of the synchrotron compared to academic use. And so there haven't been as many demonstrated useful applications of XAFs for industry as there is for basic research. I made a broad statement. There's many exceptions to what I said, but statistically speaking, what I said is right. Other questions?
That's all for right now.
All right, so let's go to a little bit longer wavelengths. And let's talk about more tender X-rays, such as if you wanted to study phosphorus, whose binding energy is much closer to 2 kilovolts instead of 7 kilovolts. Well, on the left, we have this, might even be the spectrometer that's at IIT, and it's kind of big. And then over here, we've got another unshaven grad student or former grad student of mine, and he's got a different spectrometer, and it's really small. And so on the left, you have a 1 meter Roland circle geometry, and on the right, you have a very different kind of geometry I'll only mention briefly. It looks like this. The X-ray source comes in perpendicular to the page, hits the sample, bounces off a curved piece of silicon, which spreads it out as a rainbow across a homemade X-ray camera. Okay, there's a lot of nice features about this instrument. The key thing is it's got great energy resolution, and its count rate is really comparable to data taken at the synchrotron when you're studying sulfur or phosphorus. So this is what an exposure on the camera looks like. And then when we process that and account for the little curvature here, we get out here sulfur K-alpha fluorescence and valence to core fluorescence. And it really works nicely. So this is a paper we're really happy to have been involved in. The problem is that the flat panel display you're probably looking at right now likely uses cadmium selenide quantum dots as part of the illumination. And that gives you disposal problems because of actually both the cadmium and the selenium. So there's a very broad effort afoot to try and use indium phosphide quantum dots instead, which are much more environmentally benign, but they're hard to manufacture so that they have reliable photoluminescence. Typically, you would have a core shell nanophase where you have a little roughly spherical piece of indium phosphide that you've then clad with something like zinc sulfide to protect it from the outside environment and to engineer the band structure at the interface and whatnot. And the hypothesis was that the reason why some quantum dots, indium phosphide quantum dots, are better than others was how good a job you did of preventing this from happening, of preventing getting phosphate defects at the interface between the indium phosphide and the zinc sulfide. Okay, so you have a hypothesis that the phosphate defects are important, but this is a buried interface, not an exposed interface. And that means that XPS really isn't going to be able to tell you much. The electrons can't get out through the zinc sulfide. 31 phosphorus magic angle spinning NMR can tell you about the phosphate defects, but it's slow and requires large amounts of sample. So we decided to try to use our instrument on this problem. The first thing is the fluorescence line, this 2p to 1s fluorescence, has a nice simple shift with oxidation state, right? As you tear electrons off of the valence level, you slightly decrease the screening of the 1s shell from the nucleus, and so the binding energy goes up in the simplest explanation. All right, so here's the magic angle spinning NMR, 4 days with 100 milligrams of sample. This says it's 54% reduced and 46% oxidized. With the emission spectroscopy in an hour in a small sample, we get 51% reduced and 49% oxidized. This is with an error. And we took it was a lot faster for this simple measurement of just oxidation state of the phosphorus. So, you know, this is being used as part of analytical chemistry. We're not replacing the synchrotron, because what was needed here was immediate measurement day after day for a few weeks for routine characterization as our collaborators were figuring out new material synthesis. And you just can't go to the synchrotron day after day for this kind of application. All right. So the last two things to mention very briefly is teaching. The company EasyZaps and my group at University of Washington have gotten an NSF small technology, I can't remember what it's called, STTR. It's like a small business innovation grant, where the company is going to learn how to build a little prototype system that we put together at UW, which gave this data using very simple, inexpensive parts that could be put onto anyone's X-ray diffractometer. And at the same time at UW, we're going to make teaching material and try to bring Zanes into the college level curriculum in chemistry, chemical engineering, material science, and so on. And a question for you students and teachers who are here is, you know, how would you learn or teach Zanes to college students, and what curriculum material is needed, and so on? So to conclude now, we have this hypothesis that it'll take years to figure out that 99% of all potential XFs and XES applications can happen in the lab. And this encompasses a lot of things that just don't fit with the synchrotron access model. And here's some examples of things we've done, and I'm curious to hear your ideas and your questions.
Well, I would say let's thank our speaker, but I have no idea how to do that. So if you want to share applause in the chat window or something, I'll give it. I should be careful because I can't spell it all, but we'll go with applause. Woohoo. You got a clap, clap. Very good. I have a quick question. On the low energy system, what is the energy range?
You get limited by the backscatter energy at silicon 111 to just a little bit below the sulfur K fluorescence. With silicon 111 or germanium 111, we've gone from sulfur up to the uranium M4 or M5 lines at like 3.5 kilovolts. You can go with other crystal analyzers to work at higher energies, but there's some technical problems that are going to start costing you count rate and energy resolution.
Sure. Why the reason I ask is two of the elements that I find the absolute most difficult to study are magnesium and aluminum.
Yeah.
Just an awkward energy range to cover.
Yeah, we've gotten that question. I've gotten that question a lot. Silicon also people ask about. So there are high quality crystals of quartz or other large despacing materials that if you could curve them, you could use in the same way. It's not something we've pursued yet.
Okay.
Looks like we have a question about corrosion studies.
Yes.
Yeah, so the question here is any barrier to using the technique for corrosion studies? Indeed, there are often corrosion studies done with XAFs. I think it's more often done in a fluorescence mode so that you can have more surface sensitivity at grazing incidence and can really just study the thin layer of corrosion on the surface of something. But it is XAFs is definitely used for it, but it might be a bit harder to do in the lab. And then there's another question, concentration needed to make measurements possible. Would 1% loading of metal be weight? Okay, so it's a great question. How much concentration of, let's say, the iron in a ceramic material or the platinum in a carbon catalyst you might need in order for the measurement to be viable in the lab? It really is system specific. It depends on the strength of absorption of the matrix that your metal is in. So if you have 1% platinum in on a graphite support, such as is common for catalysts, that's not so bad at all. That's pretty easy because the carbon isn't absorbing at all at the energy for the platinum. On the other hand, if you're trying to study 1% iron doped into a cobalt oxide, then that's an awful lot harder because of the strong absorption from the cobalt at the iron energy. And so you really need to go and do the calculation for each specific system and figure out how strong the background absorption is. Did that help? Other questions?
So are there any thoughts to adding fluorescence detection? I know that's one of our big issues because we do a lot of thin films.
Uh-huh.
And so it's often very difficult to shoot through it without thinning the backside significantly.
Yeah, I think it's complicated. So with the higher powered systems that are being built, it might in principle be feasible, but I'm not sure it's scientifically advisable. So as you know, Jeff, if you have a concentrated system and you're doing fluorescence mode, then you get lots of signal, but you also get self-absorption effects. So yeah, you could go ahead and do that measurement now with the high-powered system. But if you wanted it to be more reliable, you would want to work on a very thin film or a fine powder of that material. But then maybe only 1% of the X-rays are even being absorbed. And then all of a sudden your fluorescence count rate is way down and the measurement's going to take a very long time. So I think there are going to be special cases where it's possible maybe to do the fluorescence in the lab, but I think in general it's really not advisable. It's not something I've done with my equipment.
All right, thank you.
Mm-hmm. The XES, on the other hand, you can do on thin films if the thin film is concentrated, but that gives you different information.
Yeah, we were hoping to do that right before the coronavirus hit.
Yeah.
And so let me just add, if anybody wants to try samples, we would be able to do that at Illinois Tech, assuming we are ever allowed back to reopen. And so if anybody has anything they'd like to try, just let us know.
It's like there's a question from Northwestern, and my suggestion is the EasyZaps has a website, and you'll be able to find them very quickly and reach out to them for information. Okay, thank you.
Any students have any questions? Any students running into any interesting problems that X-ray absorption or X-ray emission might help them with? Well, I imagine we'll eventually get the students to talk at some point in these. We'll overcome their fear with enough prodding. We'll get them to talk sometime. But thank you very much for the talk. Any last, oh, there we go, more clapping. Awesome. Yes, thank you very much. And thanks for everybody for attending today. Any final questions for our speaker?
Well, thank you again, Jeff. Thanks for the opportunity. And in present days, it's especially nice to be able to have the feeling of normalcy, of talking with people older than my children and talking about science is really a treat. So thank you again for the invitation.
Well, we are glad you kicked this off, and I'm so thankful for you for taking time out to talk with us. I just want to let everyone know the next one will be Wednesday, May 27th. The goal will be to do these on the last Wednesday of every month. Tentatively, our speaker is Professor James Whitten from UMass Lowell. And that's going to be a more chemistry-oriented talk. And so we look forward to that one in about a month. And thanks, everybody, for coming. And unless there's no more any more questions, that's all for tonight. Thanks, everybody.
All right. Thank you. Thanks, Jeff. Stay well.
Yeah, you too. Thank you so much for doing this. Greatly appreciate it.
My pleasure. All right. All right. Cheers.